Okay. It is about time. It's uh 9 a.m. in Taiwan, 8 a.m. here. Okay, in Bangkok. Yeah. So let's get started. First, I just want to check. Can you guys hear me? I mean, you could, raise your, you know, uh, send a message or something just to let me know, like you can hear me. Okay, okay, I got your wave. Okay, good. Thank you. Okay. So yeah, first I apologize. We need to have this online course. Because I'm out of the country this week. Um yeah, but yeah, we have been we have done that like during the COVID-19 period. So to be frank, I think I'm quite comfortable with the online teaching. Okay. So and also this lecture will be recorded. So if you have any question, um at least you could like come back to um the and repeat like the part that you don't understand and get an idea. Of course, like you are more than welcome to to let me know like during the online lecture, like if there's anything you would like me to explain in more detail. Okay. Um, so let's get started. Okay. So last time, okay, we finished like some of those like advanced sorting algorithms. Uh, um, so far, how many sorting algorithms have we covered? Okay, we covered insertion sort, we covered the merge sort, and we cover the quick sort as well as the heap sort, right? And yeah, um, so all these sorting algorithms, of course, some are, I mean, these algorithms that we have covered, okay, some are like uh, more basic algorithms, such as insertion sort, okay, and actually you also have learned like a bubble sort, like from maybe like from earlier courses. So so you have learned like all these different sorting algorithms. So bubble sort and insertion sort are considered to be more basic sorting algorithms. Okay, um, but the merge sort and heap sort are considered advanced sorting algorithm. The difference is that, okay, the time complexity. Uh, the basic sorting algorithms, such as bubble sort, insertion sort, the time complexity is big O n squared. Okay. On the other hand, okay, the advanced sorting algorithm, including the um, merge sort and the heap sort, the time complexity is n log n. Okay, and we also cover quick sort, right? And the quick sort is kind of special sorting algorithm. Okay, because like it's if you analyze the complexity, okay, I'm talking about like if you are doing the worst case scenario, okay, then the time complexity of the quicksort is n squared, okay. However, if you randomize the quicksort and consider the expected or average time complexity, it is n log n. In practice, okay, as I said last time, if you want to sort like a large number of array, okay, if you don't know if you don't have any prior knowledge about it, then the quicksort is the best choice, even though, I mean, the worst case time complexity of quicksort is n squared, okay. But if you only have like a small number to sort, okay, a small amount of numbers to sort, then the insertion sort is a good choice. Or if your array is almost sorted, okay, in that case, the insertion sort also would be a better choice, okay. If you want like a performance bound, okay, such as n log n, quicksort doesn't offer that, but the merge sort and heap sort can do that. And if you want the performance bound and you don't have extra storage space to offer, then it will be heap sort. Okay, so there are all these different kinds of considerations when it comes to like sorting algorithms. Okay, so today, in today's lecture, we are going to talk about like additional, sorting algorithms. Okay, but these two sorting algorithms are kind of special. Okay, in the sense that, previously I told you, okay, advanced sorting algorithms are like heap sort and um, the merge sort. Okay, I said because the time complexity is n log n. However, okay, the time complexity of the sorting algorithms that we are going to talk about today is linear. Okay, so how could you have linear time sorting algorithms and still called like a merge sort and a heap sort advanced sorting algorithm? It's strange, right? Yeah, I mean, because the two sorting algorithms that we are covering today, okay, the counting sort and the radix sort, okay, they are based on different assumptions. They are based on different assumptions. Okay. So the previous sorting algorithms, basically, when we are doing the sorting, we compare numbers, right? Every time we make a decision, before we make a decision to do something in the previous sorting algorithms, we always compare two numbers and then decide what we do, okay, in the next step. Okay, those are are based on like sorting algorithms that are based on the comparisons. Okay, but the linear time sorting algorithms that we are going to talk about today are not like that. Okay, so this also prompts us to consider, okay, what is the lower bound? Okay, what is the best performance you could have if your sorting algorithm is based on like a number comparisons? Okay, so which also bring us to the first topic in today's lecture. Okay, Yeah. How fast can we sort? As I have mentioned, all the sorting algorithms that we have talked about so far, they are based on comparisons, okay? Because like they make decision, you know, every time they compare two numbers, okay? So all these sorting algorithms, okay, if they are based on the comparisons, then the best worst case running time, okay, would be n log n, big O n log n. Okay. So in fact, the big O n log n would be the best worst case running time if our sorting algorithms is based on like comparing two numbers. So how can we, prove that? Okay. We can, investigate this idea. Okay. This proof. Okay. We can have like a intuitive like understanding of this thing by the decision trees. What is decision tree? Here is the decision tree. Okay. Uh, this decision tree is like this. Okay. Don't look at the text. Let me see. Do you see my cursor? You see my cursor, right? Okay. So we have like internal nodes. We have the leaf nodes in this tree, right? So the internal nodes represent one comparison. For example, 1, column 2. Okay, that means we are comparing the first number with the second number. Okay, so if the first number is smaller than the second number, we go to the left-hand side. We go to the left branch. If the second number is bigger than the first number, okay, we go to the right-hand side, the right subtree. Okay, so you may ask, how equal? Okay, well, you can let's define like if two numbers are equal, then we always go to the left. Okay, actually, in this decision tree, you can assume like all numbers are different. Okay, just for convenience. Okay, it doesn't change anything anyway. Okay, so you can see that. Okay, for example, let's go to the left. Okay, assuming that the first number is smaller than the second number, so we go to the left. And again, okay, we have internal node here, right? And this time we compare the second number with the third number. Okay, if the second number is smaller than the third number, then obviously we have like a clear idea, okay, about the order of these three numbers, right? Because the first number is smaller than the second number, and the second number is smaller than the third number. So obviously the the order, okay, of these numbers will be 1, 2, 3, right? However, okay, uh, in this internal node, like 2, column 3, okay, if the third number is greater than second number, sorry, if the third number is smaller than the second number, if the third number is smaller than the second number, Okay, you go to the right-hand side, right? Right subtree. So in that case, you see, the first number is smaller than the second number, but the third number is also smaller than the second number. So you do not know, the relationship between the first number and the third number, right? So you need to have another comparison. Okay, you compare like the first number with the third number directly to tell they're which one is smaller. So if the first number is still smaller than the third number, then based on the comparisons result of the previous internal nodes, we know the order of these three numbers will be 1, 3, 2. Otherwise, okay, if the third number is smaller than the first number, then the order of these three numbers will be 3, 1, 2. Right? Yeah, so basically, the similar idea holds for the other half of the tree. Okay, so we call this thing a decision tree. So you could see that any leaf nodes will represent the situation of the order of your numbers. Okay, so or you can say the permutations of numbers. Okay, and the internal node represent basically each internal node represent one comparison. Okay, so of course this particular decision tree that we present here, okay, is a special case in the sense that we only have three numbers, right? But you could imagine, okay, this idea can be generalized into, n numbers, okay? So add the leaf node, okay, okay? Each leaf node will represent, the relationship between the numbers, okay? Which one is the smallest one, which one is the second smallest one, and so on, okay? And the internal node represent one comparison. Okay, so this thing can be generalized. I mean, here we only provide like three numbers. You can generalize this thing to 4 numbers, 5 numbers, and so on. Okay. So, but of course, like when you generalize this thing into maybe let's say 4 numbers. If say for 3 numbers, how many leaf nodes do you have? Because like you could have like all different like possible order of these 3 numbers. So it will be the permutation, like the factorial of 3, right? 3, so 3 like a exclamation mark. You know that, right? So it'll be 6. Okay, 1 times 2 times 3. So it's like you see we have 6 leaf nodes here. And when n grows, this leaf node number grows also very fast, obviously, right? So when you have 4 numbers, it will be like a factorial of 4, okay? So it'll be 6 times 4, 24 leaf nodes. So you are going to end up with a kind of big decision tree. Not to mention if n increase, okay, you are going to, this decision tree is going to become bigger and bigger. So here's the example. Okay, say we have this 9, 4, and 6. Okay, so you see like, because 9 is greater than 4, so we go to the right-hand side, okay? And then we compare the first number with the third number because the 9 is still greater than 6. So we go to the right-hand side, and then you need to determine like the order between the second number and the third number. You compare 4 with 6. So 4 is smaller than 6. So we go to the left-hand side. So it becomes 2, 3, 1. So you can see this 2, 3, 1. Sorry. 4 is smaller than 6. So you go to the left. So it becomes like 3, 1. Yes. That's strange. 9, 4, 9, 6. So it's yeah. So 2 is the second number is the smallest one, and then the third number, which is 6, and the first number is the largest one, 9, right? So this is correct. So you see like this decision tree, can be used to represent all different configurations of your input sequence. Okay. And if you want to sort these numbers, okay, you could do something like this. Okay. You go up from the leaf node, you go up. Okay. So for example, okay, 2, 3. Okay. Let's go back. 4 is already smaller than 6. Great. Don't do anything. Okay. And then, okay, go up one level again. 9, 6. Well, 9 is greater than 6. So obviously, you need to do something to correct that. Right? Okay. And again, you go up to the top. 9 is greater than 4. Again, you need to do something to correct that. Right? In order to produce a sorted sequence, okay, from 946 to 469. So basically, okay, you could see that, okay, because like I mean, this decision tree can be used to represent any comparison-based sorting algorithms. Okay, and the the of course, I mean, remember, I say, I mean, I just mentioned like 2, 3. I mean, 9, 4, 6. I mean, when you start from the like the leaf node, you go up, you go up, you go up, right? So, I mean, you go up, you need to encounter like a comparisons, and also like if the comparison is not exactly what we expect, it's not like the first one is smaller than the second one, then we need to do something, right? Let's forget about those actions, the number of the additional action that we need to do. Okay, just consider the comparisons. Okay, so obviously the number of comparisons will be bounded by, the number of internal nodes. Okay, from the leaf node to the root, right? So I said, a decision tree can model the execution of any comparison sort. So of course, okay, different sorting algorithms has a different logic, okay, to to rearrange numbers, but okay, you could arrange the you could always use a decision tree to represent your sorting algorithm. Okay, so I mean, of course, and also I mean, you have one tree for each input of size n, and that one tree should work for any input of size n for that particular sorting algorithm. Okay. So if we try to see, okay, the number of comparisons, you will see, like, as I said, like, if you have a input sequence, okay, in order to make a rearrangement, to make it into a sorted sequence, you go from the leaf node to the and so basically, like, the running time of the algorithm is the length of the path taken, which is from the leaf node to the root. Okay, so the worst case running time, okay, if you use this way to consider the comparison-based sorting algorithm, then the worst case running time will be the height of such a decision tree. Is that right? Because we are considering the worst case. Okay. So if you agree with this thing, okay, then okay, we would be able to derive that any decision tree that can sort elements must have height, okay, n log n. And this proof is kind of straightforward, okay, because the tree, okay, we know, like, as I told you earlier, okay, if you have numbers, then the number of leaf nodes would be, uh, um, the factorial of n, right? Because each leaf node represent, one particular, a sequence of particular order. But what should I say? Why do we use greater or equal? Because for every possible sequence, you must have at least one leaf node to represent that, right? But you could, I mean, for the same configuration, okay, you could end up with, like, more than one leaf nodes. It depends on how you design your sorting algorithm. Okay. For example, okay, remember, like, I told you, like, in this particular example, okay, if you go all the way to the left, like, you no longer need, like, additional comparison, and you already know, like, the order of this sequence will be 1, 2, 3, right? Because it's smaller than 2, 2 is smaller than 3. But if the algorithm was not designed, I mean, smart enough, then you would have thought that you still need to compare, because you compared 1 and 2, you compare 2 and 3. So you may, for example, need to compare, like, uh, 1 and 3, for example. But regardless of the result of 1 and 3, I mean, it must go, to a left-hand side, right? I mean, it's impossible for that to go to a I mean, you must go to left-hand side. It's impossible to go to a right-hand side. But regardless, what I'm just trying to tell you is that, okay, if your algorithm, if your sorting algorithm was not designed, carefully enough, it is possible, in fact, very likely that, the same, input sequence configuration could end up with multiple leaf nodes. Okay, so that's why. Okay, I say like the tree must contain greater or equal factorial of n leaf nodes. Okay, so yeah, let's consider the lower bound, which is factorial of n, right? So so the height H binary tree, okay, must have smaller or equal to 2 to the power of H leaves. This is something we learned from your data structure class. Okay, I hope you did. Okay, I hope you have learned that. Okay, so in other words, okay, the factorial of n must be smaller equal to 2 to the power of h. In here, okay, the h represent the height of the tree. So you can see clearly there is a lower bound for the height of the tree. Okay, so if you take log on both end, okay, you know like the right hand side 2 to the power of h after you take log. Okay, assuming the base is 2, you get h, right? So that will, that's the h you get here. And the left-hand side, log, like a factorial of n, that's what you have here. Okay. We can take log and maintain this small or equal sign relationship because log is monotonically increasing. Okay, as long as your n is greater or equal to 1. Okay, so we have this, but you may ask, what is factorial of n? I mean, you have no idea, but we know like there's a Stirling formula, okay, which can be used to approximate the factorial of n. Okay, so I'm not saying like it's exactly the same, but it's a good approximation. And also, by the way, it guarantee, okay, the factorial of n is going to be, greater or equal to n divided by e, okay, to the power of n. Okay, so this we maintain this greater or equal sign. Okay, because we also use log n here. I mean log here. Okay, so factorial of n is greater or equal to n divided by e to the power of n. So with that, okay, obviously you can apply log to here. I mean you put a exponential to the front, and you become like a log n minus log e, right? This log e is because the log here is base 2, so obviously like log e is a constant. Okay, so this n times a constant is a linear term, but the first term n log n obviously has a higher order, so we know like the height is greater or equal to omega n log n. So this is like a lower bound. Okay, it's a lower bound of the height of such a decision tree. Is okay? And with this in mind, we'll have the query. Okay, heap sort and the merge sort, because their time complexity are already n log n, okay, big O n log n. So they are asymptotically optimal comparison sorting algorithms. Okay. But of course, like I mean, here we are talking about like in terms of complexity, okay, in terms of time complexity. But in reality, like eh, you know, if you if for large amount of like numbers, you still prefer to use quicksort, okay? Yeah, because the expected time complexity of the quicksort is good, okay? But quicksort is not a asymptotically optimal comparison sorting algorithm, because when we talk about asymptotic uh, optimality, we are talking about the order of the worst case. Okay, so that's why we exclude the quicksort from this this corollary. Okay, so so far so good, right? So any question with this you know decision tree explanation? Okay. Yeah, I don't see anybody raise hand. I mean, if you have any question, raise your hand. And I mean, of course, like you may ask your question, no problem. Okay. If you don't feel comfortable speaking, you can type your question. I mean, there's a message box. I would check from time to oh, let me see. Yeah, I mean, this just content like uh uh there's no question here. But I will check like your message box from time to time in case if anyone asks question. Okay. Okay. So 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 obviously, this decision tree model, okay, can be used to explain any comparison-based sorting algorithm. But you could have a sorting algorithm that are not based on comparison. How come? Okay, here, okay. Let's consider this sorting algorithm. It is actually very, very simple idea. Okay, but it performed well. Okay. So here, okay, you have n numbers stored in the array A. Okay. So be careful here. Okay, we assume the numbers you want to sort is in the range of 1 to k. In the range of 1 to k. I mean, this k could be smaller than n. It could be larger than n. Okay. When k is smaller than n, obviously, because you have n numbers, and these numbers are range. I mean, they range like from 1 to k. So if k is smaller than n, you could obviously imagine there must be some numbers that have the same value, right? I mean, it's just like the one direct application of pigeonhole principle, right? 各种原理嘛，对不对？I suppose you have learned that from your discrete math class, okay? So So there's such an assumption. Okay, we have like the numbers are in a particular, range. So we are going to, so this is the input that, we are going to output, the sorted result to another array B. Okay, of course, the array B has the same size as the like input array. Okay, and we have this auxiliary storage space. Okay, we call this array C. Okay, the size of C, this auxiliary array, is of size K. So if run it's from 1 to K. Okay. So this is the counting sort. I will let you thinking. By checking out this algorithm first. I understand that this algorithm may not be easy to understand. Okay, why? Because like there are too many, parentheses inside parentheses. Okay, you see like you have like actually 4 loops. Okay, and the most difficult part is probably here. It's a AJ, and the result you put the result as index of C, and that result you will use it as index of B. So it looks crazy, right? It looks crazy. Okay, so what exactly is this algorithm doing? Okay, even though these four loops looks very simple, because usually a lot of sorting algorithms will have at least like a nested loops. Okay, well, we have nested loop here. Yeah, but it's oh no, this is not nested loop. So you see like counting sort does not have any nested loop. It just contain like 4 simple loops. Okay, so the first loop is quite straightforward, very easy to understand, right? Because like you just try to initialize the auxiliary array, okay, to assign 0 to every element in the auxiliary array. Okay, and then the second loop is like perhaps like the why this sorting algorithm get its name. Okay, basically, you just try to put the number, try to count how many uh, uh, numbers a particular value occurs in the list in this sequence, okay, by using this for loop. It's very, very simple. Okay, and then you do like the third and the fourth are probably a little bit like difficult to understand. Yeah, let me use like let me use an example, and then I'll come back here. Okay. So here's an example. 41343. A very, very good, very, very simple example, right? So we have A, we have B, we have C, okay? Remember, B is where we put the sorted result, there, okay? And the C is the auxiliary array, okay? So, and obviously the size of this auxiliary array is 4, right? Because like you see like we have like these numbers range from 1 to 4, right? So initially for the first loop, you need to initialize this array C to be all zeros, right? This part is quite straightforward and easy to understand. And then we do the second loop. In this second loop, okay, basically you see, when you see, I mean, because this is like a loop, I mean, to run from index 1 to index n, so we start from index 1 to index n in array A. So the first element we encountered is A1. So A1 is 4, right? So, you know, we try to increment C4 by 1. Okay, so you count, oh, there's a 1, 4 there. And then you go to the next one, okay, the index 2. Okay, here, okay. And you say, oh, there's a 1, 1 here. So you increment like the index 1 in array C by 1. And then you increment like a 3, okay, here by 1. And then, oh, there's another 4. So increment 4, you know, from 1 to 2. And the 5, okay, it's another 3. So you increment 3 by 1. So that's the result. Okay, that's the result of the auxiliary array after we finish this for loop. So obviously, at the end of this loop, you can tell that the auxiliary array store the count of each number or number of occurrences of each index, I probably should say, okay, in the sequence. Is that right? We have 1, 1, no 2, 0, 2, and 2, 3, and 2, 4. Is that right? So, then it's the third loop and the fourth loop. Okay. Before I explain the third loop and fourth loop, if you are for any like a student who has learned how to do programming, you can probably say, oh, this is easy, right? I mean, because you already have this information, okay, in array C. So you can say, I just output 1, 1, and the 0, 2, and the 2, 3, and 2, 4. I'm done with the sorting, right? So you can directly output these numbers from C, you know, to the array B in the sorted order, right? So why do we need to go through the hassle of 2 additional loops? Let's finish those 2 additional loops, and then we come back to this question, shall we? Okay. So then, okay, in this the third loop, okay, we start from the. I mean, this is like we are doing this for like array C. Okay, so we start like from index 2 to K. Okay, basically we try to, you know, do like a accumulated count. Okay, so for example, we start from the 2, right? So basically, I mean, it'll be like you know, 1 plus whatever was in like the second index. So it'd be 1 plus 2 plus 0. Okay, 1 plus 0. Okay, this is 1, this is 0, right? So we get 1. So this, okay, its meaning. What does it mean? It means that like you know, the number of counts, okay, for the values that are smaller or equal to this current index. So you can see like you have in this in the input sequence, you have one number that's smaller or equal to 2, right? Which is 1, right? And you keep doing that. That's, I mean, once you understand that, it's very straightforward. Okay, you just add this 1 to 2, so it becomes 3. So again, I mean, the direct meaning is, okay, here like well, all these numbers. I mean, you have like 3 numbers that, you know, are smaller or equal to 3. So because you have 1 1 and the 2 3, right? Yeah, 3 numbers. And then you go to like index k, and the 3 plus 2 is 5. Okay, so all these 5 numbers, they are smaller or equal to 4, obviously. So this C, okay, auxiliary array now holds like this accumulated accumulated count. Okay, basically like you know, for each index, it holds the number of the values in the original input that are that is smaller or equal to, that are smaller or equal to the current index. Okay. And then, okay, we're done with the third loop. Okay, the fourth loop. The fourth loop, okay, basically, okay, what do we do here? So we're trying to move the element from A to B. Okay, but now we are doing it in the, what should I say, in the opposite, direction, because J index from N to 1. So we first look at the 3. Okay, look at this value. Okay, so AJ is a 3, right? So AJ, okay, you look at the C, okay, C3. C3 is here, right? It's 3. So this as I said, this is like this indicate like the numbers that of values that are smaller or equal to 3, right? So in other words, okay, you should put this value in the third position, right? In the third position of array B, right? So you copy this one to here. And then after this copy, okay, you decrement this value 3 by 1, because you have done, you know, 1 3. So in other words, like after that, okay, you have, so you can sort of like disregard this number. For the rest of numbers, okay, you only have 2 numbers that are, you know, smaller or equal to 3. Okay. But you may argue, oh, then we should also decrement like a 5 by 1, right? I mean, that's because I try to explain to you like that the meaning of this this value represent like accumulated number of values that are small or equal to this index. But after we get this, what we really use them, how we are the index, the last index of that value should, you know, be moved to. Okay, so for example, like if you see a 3, it should be moved to the index 3, and you know, then well, after that you decrement this by 1. And but the 5, okay, this one, okay, the index 4. I mean, you have a 5. I mean, sorry, if you have a 4, you should still, you know, assign that to the location 5, right? So this one should not be affected. Okay, so So anyway, let's continue. And then we go back one position, okay, for 4. Okay, this 4, okay. Obviously, I mean, you check like index 4 is 5. So it tells you like you should move this 4 to index 5. Okay, and then you decrement this 5 by 4 by 1, so it becomes 4. So keep doing that. Okay, the next one 3. So you move 3 to like the index 2. You copy that to index 2. And the next one is 1. You copy that to index 1 because this here I mean it indicates 1. And the decrement is it becomes 0. Okay. And then the last one is 4. You copy it to like index 4 and decrement by 3. You're done. You're done. So this 1, 3, 3, 4, 4 is the sorted sequence from the previous I mean the original sequence. So this is the the idea of the force loop. I mean, I understand like this like you have like we chain like this index like 3 levels. So it's like it looks kind of ugly, so that's why it is like very easy to get confused. Okay, I fully understand that. Okay, if you can get this, in the first try, congratulations. I mean, you have the nature of computer programmer. Okay, you is you have the talent. Okay, I can only say that. Okay, but basically, like it's a it's a pain in the neck. I mean, if you have like a, for example, if you have like an index like a inside index and inside index, it's if your structure is like this, it's just like very easy to get lost. Okay, but back to my original question. Back to my original question. When we have this, um, when we have this, we are already able to output the sequence in in a sorted or fashion, right? You just output a 1 1, output 2 3, output 2 4s, and you're done. You can just produce the sorted list from the auxiliary array. Why do we need to go through the hassles, I mean, of the 2 additional loops? The first question is that, okay, these numbers, even though we treat them as just I mean a sequence, okay, what they really represent could be what should I say, like the an attribute of a large record. Okay, for example, these numbers could be your student ID. Okay, but we know like in a database, okay, student ID is just one attribute, right? The student ID, record, obvious. I mean, student record. One student record comes with not only the student ID but also the name, maybe your major, and your rank. Okay, you are freshman, you are junior, you are senior, and like maybe like your grades, in every classes. So these numbers, even though here we only I mean see these 5 numbers, but each number may be associated with a large record, right? But this auxiliary array, we only deal with these numbers. They are not associated with the the large record behind the scene. Okay, so when you do the sorting, eventually you should still copy, whatever in array A to array B, not doing this, sorting from C directly to B. Okay, because even though, as I said, like this copy looks just simple, you just like you're just copy a number, but in reality, when we really use this counting sort, most likely, okay, you are moving not only this number, but also the record, the large record that is associated with this number. Okay, you also copy that to here. Okay, so that's why you don't, you don't just directly output those things from the this auxiliary array. Okay, that's the first consideration. Okay, there's a second consideration there. Um, yeah, I think we will go get to that point later. Okay, we'll get to that point later. Okay, because we are going to discuss this like with other things. Okay, so well, it's already past 9 o'clock. Let's take a 10 minutes break. Okay, when we come back, okay, we'll continue whatever we have. By the way, because I'm like abroad, so I'm thinking like maybe what should I say like well, depending on like our progress, you know, uh, we could like cover maybe more material like because I saved some time like walking around like a classroom, right? So if the time allows, we could cover a little bit more material, then we will do that. Okay, depending on like the progress. But yeah, I will not rush the lecture. Okay, so is it okay so far? Any question? I mean, yeah, as I said, we are taking like a 10 minutes break, right? Let's come back like 9:15. Okay, 9:15. So during this break, short break. If you have any questions, you can also type it in like message box. Okay, and I will be happy to entertain your question. Okay. Okay, so let's let's take a short break now. Okay. Okay, it's about time. Let's continue. Okay, but let me check. No, no any question? Okay, okay, that's fine. So let's continue. Okay. So first is the time complexity. So as the time complexity is very straightforward, right? Because this, I mean, we are only talking about four very simple loops. The first loop is we run it k times because it's like a loop for like a auxiliary array. The second loop, we run it like you know n times because we are doing this for like array A. Okay, we are doing the counting. The third one we run it on array C. So again, the size is k. Okay, the fourth loop, yeah, I mean it's about like putting the numbers, putting the record at the right place. So it's like a big theta, and so in total it's a big theta n plus k. Okay, where n represent the number of numbers in the input sequence, and k represent the range of your um, values that you would like to sort. So if k is is a is a linear to the size of the input array, okay, then counting sort basically takes a linear time, right? So uh, but we know like from the previous decision tree discussion, okay, the worst case, the I should say the best worst case performance of any sorting algorithm is n log n, right? So why is it, even faster than n log n? That is because, okay, this counting sort have no comparison of two numbers whatsoever, right? So basically, okay, the counting sort, okay, is the first algorithm that you have learned. Okay, I mean, including like data structure, I mean, uh, that is like that will run in linear time. Okay, assuming that the k, okay, the range, okay, of these values, okay, is not too big. Okay, so it's because it is not based on comparison. In fact, okay, as I said here, not a single comparison between elements occurs in the counting sort. Okay, we just try to move the numbers to move around, right? Based on its value. So yeah, it's a kind of interesting, right? Because if you think about the basic idea of counting sort, it is really, really simple and straightforward sorting algorithm. Okay. But there's a catch. Okay. There's one catch here. I mean, I just mentioned to you like if k is linear to the number of elements, yeah, everything is good, right? But think about this. I mean, remember like the example I just used, okay? I was talking about like a student's ID, right? Student record, okay, and the key is the student ID. So if you really consider the real application, I mean, do you remember your ID? I hope so, right? I mean, if you don't remember your ID, I hope you at least remember your, you know, the身份证号码, the ID, your personal ID number. Okay, so you know like regardless, I mean, it's a student ID number or personal ID number. It is usually a long number, a big number to be exact, right? Right. So actually, okay, the real number for records that we want to deal with, okay, the values are usually much larger than this 41343, you know. I mean, these are really small numbers. Okay. So having said that, you know, really to assume K is you know is linear to N. Okay, this thing in reality may not be the case. Okay, that's the first thing. Okay. Second, okay, look at the C, this auxiliary array. This C is like of size K, right? Of size K. So think about this. Uh, um, if you are, again, let me use like a student ID or personal ID as an example. Okay, if you have like in a school, okay, at NCU, okay, how many students do we have? I think like an active student number is bounded by 20,000, right? Not too many, 20,000 at most. I think we have like a between 10,000 to 20,000, but I don't have the exact number. I only know like in our department, the active number of students is roughly 1,000, you know. So, you know, if you try to calculate like all the student from all department, okay, including all like undergraduate, graduate, okay, it should be like less than 20,000, maybe around like 15,000. So that's your N. Okay, that's the numbers that you probably need to sort. But in that case, I mean, if you try to sort these students and you consider their ID, oh, ID is like tens of million, you know. So you need like this auxiliary storage. You need a very large auxiliary storage, right? In reality. So again, that presents an issue, okay, to allocate such a gigantic storage space for your auxiliary like array. Okay, so yeah, so counting sort like is good, it's simple, but it has the such an issue. Okay, actually, this issue will be mitigated. These two issues will be mitigated. Okay, after we talk about another, you know, non-comparison based sorting algorithm. Okay, radic salt. Okay, but let's forget about that. Okay, let's continue our discussion about counting salt. Okay, we will finish counting salt like maybe in another few minutes. Okay, and another important nature of the counting salt is that it is a stable sorting algorithm. What do we mean by stable sorting algorithm? What is a stable? What do you mean by what is the definition of stable sort? Okay, we know like when we sort numbers, smaller numbers should be moved to like the to the front, right? Small number will be moved to the front. That's for sure. And large number will be moved to the back of your array, right? That's not an issue. That's not something that we are discussing here. What we are discussing here are if you have like some values, okay, that are repeated in the input sequence. If that's the case, sometimes you want to preserve, their, their order after you sort these numbers. For example, let's look at like this the example that we just went through. Okay, 41343. Okay, and this B is represent like the result of the after the counting sort, and this lines also indicate like where these records are moved from their original places. And you can see that, okay, for example, because in this list, we have 2 3s, we have 2 4s, right? Let's have a look. These 2 3s, I mean, the 3 in front, I mean, the first 3 is moved, okay, to the second index. The second 3 is moved to the index 3, right? The third index. So this in the original sequence, I mean, this 3 is it appear, I mean, in front of this 3. So at a sorted in a sorted sequence, this 3 is still in front of this 3, right? So this is not a coincidence because we have 2 4s, right? And you see like this the leading 4, okay, end up at index 4, and the second 4 end up in the index 5. Again, like you know the 4 that appear in the front of the sequence in the original input, okay, remains to be in the front. Okay, that is the meaning of stable sort. So stable sort will maintain the order of the of the same values in the input sequence. So that's like a stable sort. Okay, and think about this. Why does the counting sort have this nature? Why does the counting sort why is the counting sort able to be a stable sort? Let's go back to here. That is because in the fourth loop, we are putting, we are doing this, from the behind, right? From the back of this input array. And, we try to put like these numbers, using the accumulated index, where like, we will start by using like a largest index of this number, because we are doing this from the backward, in the backward order, in the backward manner. So this fourth loop actually is designed carefully to maintain that stable sort property. This also is another reason, a second reason why we don't directly copy from from the auxiliary array. To make the sorting like a sequence. That's because, okay, we want to make sure the counting sort is stable sorting algorithm. Okay, so naturally we will have like a question to answer. What other sorting algorithms that we have talked about maintain this to have like a stable sort? Anybody tell me? Is the insertion a stable sort? Yeah, merge sort is somebody answer. Yeah, good. Merge sort is a stable sorting algorithm. That's correct. Okay. Insertion sort. How about insertion sort? How many of you think is a stable sort algorithm? Nobody? Actually, like insertion sort is also a stable sort algorithm. Okay. In fact, the if you design the algorithm sorting algorithm careful enough, okay, the only sorting algorithm that we cannot guarantee the stable sort property so far is the quick sort. Okay, so most of the sorting algorithms enjoy this property except the quick sort. Okay, I would let you think why, why, some sorting algorithms are stable and why, quick sort is not a stable sorting algorithm. I will let you guys think by yourselves. Okay. It makes a good, like, brain teaser. Okay. And, yeah, I will, anyway, yeah. Just want you guys to understand, okay? Most of sorting algorithm, except the quick sort, okay, are stable sort algorithm. So now we move to the second non-comparison based sorting algorithm. This is also like a sorting algorithm that has a very good nature, and it has a linear like uh time complexity. Okay, it's quadratic sort. So its origin is the Herman Horowitz car sorting machine. Okay, so because like 18 in the year 1890, okay, United States is doing like a census 人口普查啦，人口普查。So so they need to be able to efficiently sort a large number of cards. Okay, a large number of cards. So this guy, okay, the Herman Horowitz came up with this idea, okay, relic sort. So this relic sort actually sort numbers digit by digit. Okay, digit by digit. And it turns out that this is a very powerful sorting algorithm. Okay. But of course, like I probably should have pointed out, like Horowitz' original idea, okay, about this relic sort is is problematic. Okay. Um, he tried to sort on the most from the most significant digit. OK，也就是说，譬如说你有一些数字啊，就是好几个位数的，它从最左边开始，那个最左边一位开始排序。But as we will see later, okay, this is actually not correct. It's not correct. If we sort from the least significant digit first, in other words, like we sort from like right to the left, then there's like some property we can use to prove that this sort result in like the sorted sequence. Okay, we can prove that. Okay. So first thing, okay, okay, the relic sort also depend on another sorting algorithm. Okay, this other sorting algorithm, okay, first, it has to be a stable sort. Second, okay, it doesn't have to be, it will deal with a large number of sequence. Okay, I mean, you will have a lot because you are doing like a census, right? Like, so you have a lot of cars. So yeah, I mean, the N is large, but the K, because like every time you are sorting one digit, right? So let's use like our like decimal numbers as example. Okay, each digit only has 10, you know, possibilities, right? From 0 to 9, right? So in other words, your K is small, right? Your K is small. So because N is large, K happens to be small. Okay, so it seems to everyone that counting sort will be the best option to go with the relic sort. Okay, so yeah, I mean let's talk about this. I mean, later. Okay, let's first. Oh, by the way, I mean another thing. Okay, that I would like to point out. Okay, because this is used for like to sort the cards, right? Okay, initially it was designed for like a U.S. Census, right? But in the early age, computer use card readers. You know that, right? I mean, I understand. Like, I mean, you guys are too young. Okay, you don't see like those like the mainframe machines that read card. That's just you know, at the time when you were born, I mean, I think the last such machine has retired a long time ago, you know. Um, yeah, I mean, at the time when I was born, like, of course, there was, I mean, many such machines. But at the time when I study computers, or at least like when I was like an undergraduate student, okay, I mean, I was at NTU, and NTU has a machine called VAX machine. Okay, that's still like a what they call like a mainframe or like a supercomputer. Nowadays, nobody use supercomputer. Like we have like a server, but server, I mean, the architecture of server is different from supercomputer. Supercomputer is a special design architecture, you know. So so at my age, I still see supercomputers, but and I still see like operating systems as specially designed for supercomputers. But yeah, for example, VAX machine, they are using a different like operating system. It's a pain in the neck, okay, to use. I use it like just a few times, but and I gave up because I was the my major was like math. You know, I didn't I was not required to do a lot of like programming anyway. You know, but but I have to tell you, like you guys like nowadays like the computer becomes so easy to use. You know, you have like I don't know, are you using Windows or Mac? You know, whatever it is, like it comes with a lot of like GUI, the graphical user interface, right? So the computer becomes like a relatively easy to use. But I mean, at the time when I use the computer, it's I understand like yeah, it's difficult. I mean, compared to your environment, but my case is still much better than like a mainframe that reads like in like cards. You know, I think like my advisor, okay, my advisor at Ohio State University. I mean, at that time, like when he studied like a PhD, I think it was like 1970, 1980s. Okay, 1980s. I mean, he was like using the card reading machines. Okay, card reading machines. So this Reddick sword is also, has also like a big applications for those card reading machines. I should say card reading mainframe. Okay, so this Reddick sword, is like very very important sorting algorithm to say the least. Okay, so what is Reddick sword? Let's have a look at the example. Okay, I think yeah, it's already 45. So let's look at this example and we'll take another break. Okay, so here, okay, is how we perform the Reddick sort. Okay, so we will sort one digit at a time by using the stable sort. Okay, so at this moment, forget about like how you sort these numbers. The only focus is first, of course, you focus on one number. Second, you focus on, this sorting algorithm has to be stable. In other words, like if you have two numbers that have the same digit, the number that appear in the front has to, stay in the front. So for example, you see, okay, we start from the left-hand side. We start from here. So you see like, because we start from the first digit, right? So 9779605. So obviously we have like 2927s, right? So obviously this 720 appear first because 0 is the smallest one. And then we have 355 because 5 is the second smallest one. and then 436 because 6 is the third smallest one. Okay, and then we have 27 and 29, right? But you be careful. You see like because 457 appear earlier than 657, so you have 457, 657, this order. And for those 29s, obviously 329 appear earlier than 839, so 329 will be in front of 829. Okay, so we're done with the first digit. Then it's the second digit. Okay, so in the second digit, you have 2535523, or a lot of repetitions. Okay, we have two twos, right? We have two twos and two threes and 1, 2, 3, 3 fives, right? And so we will put these two twos first. But these two twos, obviously 720 appear earlier than 329. So we put 720 ahead of 329. And then, okay, it's about 3. So obviously 436 appear earlier than 839, right? So 436 appear earlier than 839, okay, here. And then we have 3 fives. Okay, the first 5 appear to be 355. So 355 appear to be the first one. And then it's 657. Oh, sorry. Then the second one is 457 and then 657. So we have 457, 657. So now we are done with the first two. And then the last one, 7348346. So we have two fours, we have two threes, we have two threes, two fours. And those two threes obviously are the smallest elements. So we put the 3 first. And the 329 appear earlier than the 355. So it's 329, 355. And then we have two fours, two fours. So 436 appear earlier than 457. So we put 436 and then 457. And then what else? And 3, 4, and then 6, 6, 7, 8, right? So 1, 6, 1, 7, 1, 8. So that's straightforward. So we are done. And look at the order. 329, 355, 436, 457, 657, 720, 839. So these 3-digit numbers, they are already sorted, right? That's the radix sort. The basic idea, we sort one digit at a time from the least significant digit to the most significant digit. Okay, one digit at a time by using any stable sort algorithm. Okay, any stable sort algorithm. Mostly, I mean, counting sort. Yeah, but yeah, it's not confined by the counting sort though. Okay. So yeah, have a look here. Okay. So let's take a 10 minutes break. When we come back, we'll talk more about radix sort. Okay. And of course, like if you have any questions, you are more than welcome to, type it in uh, 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 message box, and I will entertain your question after we come back from the break. Okay? Thank you. Okay, let's come back to the lecture. Okay. Yeah, good. I see like some questions, okay, in the message box. First, um, yes, hip salt is also not stable. Okay. Why hip salt and quick salt are not stable? I want you guys to think about it. Okay. And try to come up with scenarios that, I mean, to explain why they are not stable. Yeah. So that's to answer the first question. The second question, uh, um, uh, actually, I have issue understanding the question. What's the difference so between sorting with most significant and radix and the least? Oh, you mean like I think like your question may be related to like why don't we start from the most significant one, right? From most significant digit to the least significant one. Okay, why don't we sort like from the other direction? Okay, yeah, um, uh, I think like it will become more clear, okay, when we explain, when we talk about like why red result is correct, how we prove its correctness, okay, how we prove the correctness. Okay. So anyway, yeah, let's continue the discussion of the radix sort. Okay. So the radix sort, okay, why is it correct? Let's first come back here. Let's look at this example. This I mean, this is the initial sequence. This is a second sequence, right? In the second sequence, let's only look at the first, the least significant digit, you know, 我们只看个位数。It's obviously sorted, right? It's obviously sorted. 0567799, right? This is obviously sorted. So at the conclusion of the first loop, after we deal with the one digit, the rightmost digit, this part, the rightmost digit is sorted. No question about that, right? And at the conclusion of the second loop, okay, let's not look at the most significant digit. 我们先不要看那个百位数的。Let's just look at the other two digits. Look at here. 20, 29, 36, 39, 55, 57, 57. They are sorted, right? So at the conclusion of the second loop, after finish the second loop in the radix sort, the 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 last two digits have been sorted. 就是我们做完第一个 run 回来结束的时候，我们最右边那个 digit 已经排好了。第二个 run 结束的时候，最右边两个 digit 已经排好了，对不对？And then the conclusion of the third loop, yeah, we sort all three digits correctly, right? 对不对？所以我们其实一个 digit 一个 digit 的把它排好， Okay. Then this also explains why if you sort from left side to right side, it doesn't work. Okay. Let's give an example. Let's look at the example. Let's just use these numbers as the example because we start from the least significant digit to the most significant one, right? So let's try to do the opposite way. So we have 3, 4, 6, 8, 4, 7, 3, right? 没有黑板哦，所以有点我怎么 here? So it becomes what? 329, right? 3, how do I enlarge? 329. Can you see my typing? I'm not sure if it's large enough. Is it large enough? 329. If it's large, if it's readable, please send me a message or something. I know it's a little bit small, okay, but I don't know adjust the size of the text. I'm sorry. Okay, good. Somebody answered. Okay, at least one student can see it, right? Okay. How do I close it? Ah, okay. So 329. And then oops, the next one will be we have 329 and then 355, right? Sorry, 355. The next one will be it's 4, right? 457. And then 436. 457, 436. And then 657. And then 720. And the last one is like A39. Right? So we are sorted, right? I mean, the first digit has been sorted. Is that correct? Then based on this, let's start sorting the second, the second digit. Let me write it here. Yeah, let me write down here. Okay, down here. So the smallest is 2, right? So it's still 329. And then the second is 720, right? And then we've done with 2. And we have 3, 436. And then A39. So we're done with 3. And then we have 2, 5. 355. And 457. And anything else? Oh, 657. The last one is 657. Yeah. Done. So we have done with the second pass, right? Actually, at this moment, we don't need to continue anymore. Why do I say that? Think about this. When you do the sorting from right side to the left side, okay, at the conclusion of the first loop, the first digit has been done. At the conclusion of the second loop, the two last digits have been done, right? And so on. So look at here. At the conclusion of first loop, the first digit has been done. The first leftmost digit has been done. That's correct. At the conclusion of the second loop, do we have like the last two digits done? We have, 你看嘛, it's a 32, right? And then 72. And then it's 43. Well, it's not sorted, right? And then we have 83. And then again, we go down to 35 and the 45 and the 65. You can see that it is that the first two digits are not sorted, right? You could try to finish up like the last digit. I mean, from the left side to the right side, but obviously it's not working. Well, is that right? The issue, what is the issue? The issue is, okay, we could, the numbers, if you do the induction, you start from the least significant digit to, one level at, by the time. You can carry it over, to the top. But you cannot do it in the opposite manner. Okay. So for example, assume that the numbers are sorted by their low order t minus one digit. So say like you are done with like a previous t minus one loops. Now you are trying the t's loop, trying to get like for example, you are done with the first two loops. So you are already your numbers are already sorted based on their like previous two numbers. And now you are sorting the third digit. So you are sorting the on digit t, okay, assuming the t is a 3, okay, in this particular example. So, I mean, if two numbers have different digit t, then obviously, I mean, the smaller one will go in the front, right? For example, the 720 will appear, behind 329. That's correct, right? Even though, okay, what should I say? Like, it means 20, means 720 has 20. 329 has 29. But because the most significant digit, 329 has 3, 720 has 7. So 329 has to appear earlier than 720, right? So which is correct? One, once 19 always lost to 90, right? I mean, because yeah, this is nature, right? So if two digits are different, you put them in the right order. And if two numbers are equal, for example, this is 4, this is 4. When you put them, I mean, here, you will put them according to their, I mean, order, right? Because it's a stable sort, right? And the previous digits, they are already sorted, right? So, the stable sort guarantee that 436 will appear earlier than 457, which again will make sure the result is correct, right? So this is like there are only two cases, either like I mean, two numbers are different in digit t, or two numbers are the same at digit t. So we are able to get the job done in both cases. So in other words, this induction guaranteed we can get this, this sorting done correctly, right? So this is like very important. We start from the least significant digit to the most significant one. Okay, from the right hand side to the left hand side. Okay. So we need to analyze the complexity of the radix sort. So as I said earlier, okay, we usually assume the counting sort is used as the auxiliary stable sort algorithm for radix sort. It's because the counting sort, the issue with the counting sort is that you don't necessarily have a good bound for K, right? That's the issue. That's a primary issue. But in the radix sort, because each time you deal with one digit, right? And that particular digit obviously is bounded by a small number, right? So this is a very good property. Okay, it gives you a good bound for K. So that is why, okay, we tend to use the counting sort for radix as an auxiliary sort, counting stable sort algorithm for radix sort. Okay, but you also need to understand any stable sort algorithm work well with auxiliary, work well as an auxiliary sort algorithm for of the radix sort. Okay, it's not like you have to use counting sort but the counting sort has a good property because it's a low time complexity once K is bounded, and once K is bounded by by a small number, you don't need like a large like a additional storage either. Okay, so all is like considered. The we use the counting sort as auxiliary stable sort for radix sort. Okay, so here we are sorting n computer words of b bits each. Okay, so it's like for example, okay, if you have like 32 bits, okay, if each word is 32 bits, you can break it into like 4 8 bits. You know that, right? I hope like you guys like have taken like a computer architecture, or is it or like maybe like a 技概, right? I don't know like English for that course, but yeah, so like a word is 32 bit and you can break it like into 4 8 bits, right? So in this case, the B is 8. Okay, so each word can be viewed as having B divided by R base 2 digits. Okay, so in this case, Yeah, you are sorting. Oh, sorry. My bad. I mean, you have n numbers. Okay, let me make the question like more clear. You have n numbers, and each number, B is 32. Okay, so each word is 32 bits. Okay, or each number is 32 bits, and each word is viewed as having like a B divided by R. So R is 8. Okay, so you have like a 4 base 2 digits. Okay, so R is 8. B is 32, R is 8. Okay, so R is 8. Okay, B divided by R is 4. So because you have 4 digits, so you need 4 passes of counting sort. Okay, from the right hand side to left hand side. Okay, so that's one way to do it. Okay, if R is 8, if you can obviously also another way to set it is you can set R to be 16, right? If that's the case, the B divided by R will be 2. So you need only 2 passes of counting sort on base like 2 to the 16 digits. Okay. So yeah, for 32 bits, you can, obviously, do like 1 bit at a time for 32 times. 32 like rounds. You can do like 2 bits at a time for 16 passes. You can do 4 bits at a time for 8 passes. You can do 8 bits at a time for 4 passes. You can do like 16 bits at a time for 2 passes. Right? So you have like different. You could also do like 32 bits at a time for 1 pass. If that's the case, the rarity sort is reduced to counting sort. Okay? But anyway, you have so many choices, right? So what choice should we make? That's the question. So let's try to, first try to formulate the complexity. Okay, we know counting sort takes like a big theta, like n plus k time, okay, to sort n numbers in the range from 0 to k minus 1. Okay, so if each b bit word is broken into r bit pieces, and each pass of counting sort takes n plus, because that's k is like the range for your r bit pieces, right? So it's 2 to the power of r. So each pass takes this much time. Okay, and also like we need like how many passes? B divided by r, this many passes, right? So the total time required for the radical sort would be B divided by R times n plus 2 to the power of R. Okay, so this order. In here, the R is the variable that we could like select by ourselves. Okay, and the B and N are given. Okay, so you can see that, I mean, here. Okay, we sort n computer words of B bits each. So you can see that, okay, N and the B are given by the, by the question. Okay, so that's why T has 2 arguments. Okay, T has 2 arguments, N and the B. Okay, so, so in this formula, okay, obviously, as I said, R is like a parameter that we could choose, right? So we want to choose R to minimize this formula, okay, the order of this formula, okay. Obviously, increasing R means, B divided by R will be smaller, right? But, we are, at the same time, increasing n plus 2 to the power of R, okay, if you increasing R, okay. But as R is much larger than log n, okay, the time grows exponentially, okay. So, if, because this part grows exponentially, this part, I mean, you only like divide B by R, so it's like a linear reduction. But this part R, if you increase R, this part grows exponentially, but this part decrease like only like linearly. Well, by a factor of R. So supposedly, okay, you don't want like a too big of R. That's for sure. So one way to do it, I mean, well, you guys are, have taken like a calculus, right? From your, so, like, if you have a formula and you want to calculate like the extreme value of this formula, one simple way is, you just differentiate this formula, okay, and set that variable to 0. So you can just like differentiate this formula by R, because R is a variable here, okay, and set this formula to 0 and see like what value of R will result in extreme value. Okay, that's like what the calculus teach you, right? Okay, so another way, is like we just observe. We don't want like 2 to the power of R to be, to have like a larger order than n. Okay, so because if this is the case, then this thing will be, will have like a, higher order than linear. So that's something we don't want, So, there's no harm asymptotically in choosing R as large as possible. As I said, like subject to this constraint. Okay, because like what should I say? I mean, if you as I said, if you increase R, okay, as long as you do not increase the order of this inside this parentheses, it doesn't hurt, right? If you make this part very, very small, this part very, very big, I mean, well, still like you are not saving much because n is there. So you should try to make R as large as possible, but at the same time, make sure like it's not going to affect the linearity of this of the term inside the parentheses. So one easy way is to choose R to be log n. If you choose R to be log n, you can see 2 to the power of R will be n. So this part will be reduced to like a n, right? And the B is a constant, so R is log n, so it becomes like a Bn divided by log n. So this is pretty good, right? This is pretty good. It's like even lower than linear. Even lower than linear. So if for numbers in the range from 0 to n to the power of d divided by -1, okay? So we have like a b equal to d log n, okay? So because b, is like also known to be like d digit, okay? Your b, okay, b word, okay, your b bits, okay, the b bits here, okay. We know like it's like a digit and log n, okay, because like n is like the number it's like a number of you know the number of value in the sequence, right? In the input sequence. So if you try to assign b to be this value in here, then the log n cancel out and it's linear, where d represent the number of digits, okay, times n. So basically like it's linear because like well, the d is usually, as I say, like for example, in this case, d represents 3 digits, right? So you have 3 passes of like a counting sort, and we are able to do this each one of them as in linear. So the total analysis result is linear. So here's a conclusion. In practice, Reddick sort is fast for large inputs, as well as simple to code and maintain. Okay. Obviously, you need to implement counting sort first, and then call counting sort as a, you know, uh, procedure. Okay. In your Reddick sort. Okay. So for 32-bit numbers, okay, we do, 3 passes when sort, when sorting like greater or equal to 2,000 numbers. Merge sort, okay, and quick sort do at least, this log 2,000, so which is about like 11 passes. Okay, so Reddick sort is indeed quite fast. Okay, but unlike quick sort, okay, Reddick sort displays little locality or reference. Okay, so this is like in memory. Okay, in computer memory, if algorithm has a good locality of reference, you can use what we say like spatial temporal correlation to somehow like tune the performance to make it perform better. Okay, but quick sort can do that. Okay, but Reddick sort cannot. Okay, so there are still some limitations. Okay, I mean this is confined more like by like hardware architecture. Okay, by the hardware architecture, but software wise, okay, idea wise, Reddick sort is a good sorting algorithm. Okay, yeah. So we conclude. Okay, now we are concluding this um chapter, and 2 things to remind you. The first one is that we have the uh, um, homework uploaded. I believe like it's still like pretty soon. Okay, so I just want you to be aware and don't forget to do it. Okay, I think that the range of that homework is like it covers like up to like the end of last lecture. And let's we also have homework for this one and the next chapter, but yeah, I mean it won't be it will be given out like next week. Okay, and also the second thing is the programming assignment. Okay, the program assignment. I already asked the TA to post the programming assignment. Okay, for this class. Okay, and the first programming assignment is highly related to sorting algorithms. Okay, I want you to implement all these sorting algorithms, and I want you to run them like one step at a time to see like the performance of each sorting algorithms. Okay, and yeah, I mean, of course, like include every sorting algorithms that we talked about. Okay, and that's second thing. The third thing is about midterm. Okay, the date of the midterm will be the third week from today. Okay, today is already like let me see. What's today is fifth. Actually, today is lecture 5, but actually today is the 6th lecture, right? Because like oh no, this is fifth lecture. Is that right? Today is the 5th lecture. So we have like remember I told you we have 17 weeks. Okay, it's not 18, it's not 16. So I always take the middle one. So it's 17 weeks. 17 weeks. So we could have like a midterm, like uh, either on the 8th week or on the 9th week. Okay. So I think like because today is the 5th week. So I think like it'll be appropriate to set the midterm to be the 8th week. So 8th week, which will be like 3 weeks from today. So it's let me check. 8th week from today. No, not 8th, 3rd week from today. So 1, 2, 3. So it's going to be like April 9th. April 9th. Okay. So the midterm will be on April 9th. Please, I mean, remember, okay? And I know like some students do not come to class. If you think they are your good friend, I mean, let them know. If you think they are not your good friend, it's your freedom. But anyway, I will also ask like a TA to post it, okay, to like E class, just to remind everyone, okay. The third, which this is like it's the 8th week, okay, 8th week of this lecture of this class, okay. I mean, we could do it like on 8th week or 9th week, okay. If you guys have trouble, okay, on that day, let me know. But if nobody, you know, give me any feedback, then the midterm date will be set to be the on that day. Okay, it's August. Shoot, August. August 9th. And 1 week, I believe like I discussed with like those like undergraduate TA. They say they will set the programming exam a week after my midterm. So remember my midterm is April 9th, right? So their exam will be, you know, the next week, okay, of the April 9th. Okay. So as I already remind you guys, like at the beginning of this semester, that we have a lot of like homework exams, so you'll start seeing those things. Okay. And yeah, that's about it. So we have like less than 10 minutes. Oh, and one thing, okay, but I will not go into those slides, but yeah, I know like this set of slide has like some, how should I say, like punch card technology, I mean, it talks about like the 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 old days, okay, the old days, like the punch card, like you know what some history about computers. But I of course I will not go into the detail, but this is the guy, okay, the Herman Horowitz. But yeah, I'll skip this. Okay. For those of you interested in a little bit of the punch card history, okay, you are welcome to check out like the rest of the slides, but I will not cover this part. Okay. And then, okay, let me, let me, oh, this, sorry. Okay, that's, I know we have like just a few minutes left. Which one is which? Okay. This is also, this lecture, okay, is also has also something about like the sorting. Okay. So, oops. Oh, sorry. Can you see my slide? The lecture 6 slide. No? Shoot. How about now? Okay, good, good, good. Shoot. So this lecture also has also something to do with like sorting. Not exactly about the sorting. It's about like remember we talked about quick sort, right? So in the quick sort, we talk about like partition, right? We talk about partition. Okay. So So I think like we because it's already 46. So I think like I will only like be able to cover like what we are going to discuss, the topic that we are going to discuss in this chapter, you know, that's it. Okay. So yeah, I mean the what order statistics is really like about like finding the ith smallest element from an unsorted sequence. Okay. Again, let me repeat. Finding the ith smallest elements from the unsorted sequence that contains n numbers. Okay. You could imagine, you could assume that these n numbers are distinct, they are different, to make your you know intuition easier. Okay, to make your thoughts a little bit, consideration a little bit easier. Okay, you could assume all these n numbers are different. So we want to find like the ith smallest element, okay, or like the ith rank element from these numbers. Okay, so yeah, there are some special cases when I, is given. Okay, for example, if I is 1, that means we want to find like the minimum element from your number, from these numbers, right? And when I is n, that means we want to find the maximum element from these n given numbers. Or when I is about half, okay, either n plus 1 divided by 2, okay, with floor or ceiling, okay, that means we want to find the median out of these n unsorted numbers. Okay, first, if I want you to do that, okay, when n is given, okay, if n is 1 or n, okay, the job is easy, right? Because you just, just scan through all those numbers and keep track of, for example, if you are looking for the minimum number, then you just scan through a number, keep track of whatever the smallest number you have seen so far. And at the end of the scanning, you have the result. Is that right? The complexity of this approach obviously is linear. Okay. Similar approach can be had when I is n, right? Finding a maximum number. So those are like easy cases. But things start getting a little bit more difficult when you try to find like a median. Okay, when you try to find a median, things gets more difficult because that scanning approach obviously doesn't work. Okay, so a naive algorithm would be, well, let's just sort these numbers, right? Because we have talked about all these sorting algorithms out there. So if we sort these numbers, and it will be easy to find a number at any rank, right? So yeah, I mean, the worst case running time, okay, would be the cost of the sorting which is n log n, theta n log n, assuming you are sorting these numbers with like advanced sorting algorithms such as merge sort or heap sort. Okay, plus one, plus a constant, cost to to check out the element with index I, right? That's still like a theta n log n, right? So yeah, so that's an intuitive approach. Okay, and it works also for finding a median from these n numbers. Okay, but can we do better? That's the focus of this chapter. Okay, that's the focus of this chapter. Okay, so I think like yeah, we are running out of time. So we will we are done for the day. Okay, on this slide. So next time we will continue our discussion and finish up this lecture. Okay, yeah. So any question? You can post it on like a message box if you have any question. I don't see any. So, well, I guess it's lunchtime for you guys. Okay. So, yeah. So I will see you guys in the lecture next week. Okay? Yeah. So that's it for today. Okay. And remember what I said. Okay. The homework, the program assignment, and the dates for the midterm and the programming exam. Okay. And I will see you next week. Okay. Bye bye.
老师，那个，所以期末考试第17周吗？
对对，期末考是第17周。
好，谢谢老师。
OK，有任何问题吗？OK，好，但是你们要注意哦。OK，notice that we have two programming homework. Sorry, programming exam. OK, so which should happen 1 week after the written exam. So my written exam is on the 17 weeks, right? So the the programming exam, the second programming exam should be in the 18th week. Okay. I just want to give you a head up. Okay, don't be confused. Oh, don't think like there's nothing scheduled on the 18th week. I'm just saying like my job is done, but there are some additional work. Okay, I don't be confused. Okay, don't you I don't want to mislead you guys to think like, oh, okay, after the 17th week, I'm done. I'm going home. No, 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 no. There's something more. Okay. Yeah. So any other question? 呃，哪一种语言？嗯很显然你没有去那个城市的那个课。OK，Yeah，Python, C++. Should be fine. 然后上机考试和什么笔试大概都会考什么？Obviously, I cannot tell you. uh, I will give you a simple midterm next week. Okay, I will give you a simple midterm next week. Of course, my midterm will be different from the questions like in the simple midterm, but you can get an idea, what type of questions may appear in the sample midterm, in a real midterm. Okay, in a real midterm. Okay, so that's what I can help you with. Okay,那 but obviously I cannot tell you like我不能告诉你考试考什么。As for like a programming exam, I think you guys had a better, you know, follow up like what those undergraduate TA covered, okay, in their in their lecture recitation like session, and also like of course like the programming exam could also be something that we cover in class. Okay, open source，什么叫 open source 啊？I don't think it's 你指的是 open book 吗？应该应该有一些限制啦，不可能是，那你这样子你就直接上网去查答案就好了嘛。对，所以应该不是那个城市考试用哪种？这已经看过了。4月2号是否因为校庆活动？校庆，我们4月2号有校庆活动吗？看一下，我没有听说4月2号会停课啊，目前没有听说，目前没有听说。OK，如果有任何的变动，我会在class 跟大家讲。OK，上机考试，我刚刚讲啦，呃应该大多数的就是那种大家常用的程式语言，包括 Python、Java、C、C++应该都可以。你们真的建议你们要去一下 recitation 啊！你们如果说什么，这这个都只问这些问题，这个看起来不太妙。就是这个就是对啊对啊对啊，但是他们3个礼拜会有一次啊，那他们也会有把那个 slide share 给大家。那你们像这些问题，你们至少可以问啊，对啊，你们可以问他们助教啊，对啊，那个网站，你说是哪个网站啊？那个网站，不好意思，c++.com。这个我要跟助教讨论一下，因为我不知道这个网站。对对对，我想，就像我刚刚讲的，毕竟是考写程式，你如果说你完全不限制，那你就直接叫 LM 帮你作答就好了啊。那现在有一些 LM 已经很强了，那到底我们是在考你还是考 LM 啊？对啊，这个不太合理。所以还是会有一些限制，但是这个我会跟助教再讨论一下。4月2号停课一日是吗？你这个我看一下。哦，4月2号校际活动周，了解，好吧，那就4月2号停课。对啊，就是如果学校有规定，我们就要 follow 嘛。对对对，好不好？那4月2号停课，但是下礼拜不会停课嘛？对对对，OK，还有什么问题吗？下周二， 我们的助教课是3个礼拜一次，所以第一次是第3个礼拜，第二次是第6个礼拜。今天是下个礼拜是第六个礼拜吗？对，你们自己看哦，就这实在不需要我去讲了。对对对对，呃，好不好？这样子会影响到期中考范围，期中考范围，期中考的范围就会考到我教的哪边，这样子就考到那边这样子。对，那至于说会不会影响，那当然4月号没有上课，那就是少1堂课。那对啊，就这样子。OK，好，那就这样子喽。OK，那如果没有还有什么问题吗？如果没有问题，那我们就到这边，好不好？谢谢大家，下礼拜见。看起来你们线上问问题的那个还比我现场上课问题问的还比较多，说不定线上上课还是比较好的选择嘞。对啊，OK，好吧，Anyway，开个玩笑，那我们就在这边，不管怎样，我下礼拜会回台湾，下礼拜见哦。OK，好，拜拜。